Good morning, good afternoon, and good evening, everybody. Welcome to the second EMinar of 2021. Today we have Joel Jansen on natural source EM methods for mineral exploration. But before I introduce Joel, I'll tell you a little bit about the upcoming EMinars. So next week we'll have Paul Bedrosian on the USRA magnetotelluric program. And the week after that we have, and just like last week, I have to apologize in advance for not being able to properly pronounce this name, Pierre Wawrzyniak and Farid Smai on Razorback, an open source processing library. On the 3rd of February, Anna Marti on MT response function analysis. And the week after that, Alireza Malemir on smart exploration, new ways to explore the subsurface. I think this goes then into, yes, OSLAMP and the Australian lithosphere with Stefan Thiel on the 18th of February. And after that, Alison Kirkby talking about MT-Pi. And finally, in March, we have Doug Oldenburg and Lindsay Higgy from Canada talking about inversion and SIMPAC and geoscience. So a full and exciting program for the next month, and you can see the registration link below. Also, in case you haven't noticed, all the previous presentations are accessible, and you can watch the videos and see the recordings for anything you might have missed. And finally, I assume most of you have participated in Zoom meetings, so hopefully this is nothing too new. There are a few settings that you have to be aware of. Probably the most important one, if you can hear and see everything now, is the Q&A button. So if you press that, you can enter some questions that will appear in a special box to me and Joel. I'll keep monitoring what you enter. So if you have a question that you would like answered during the talk, don't hesitate to put something in, and I'll flag that. Otherwise, we'll have enough time for questions at the very end. And yes, with that, I would like to introduce our presenter today. So Joel Jansen is a geophysicist or lead geophysicist with Anglo American. He's been working in exploration geophysics for about 25 years now and has worked, as I understand it, pretty much all over the world. Mexico, Chile, parts of Africa, Australasia, you name it. Before he was working at Teck and actually a few other mining companies, and he has a master's in engineering geophysics from Queen's University. So I expect some interesting insights and into, well, exploration geophysics, the role of EM, and sort of how things work in industry. And with that, I would like to hand over to Joel if he's around.
I'm around.
Great.
Okay, thanks. So I will share my screen now. And you will tell me if it's working for you.
Actually, I don't know if yes.
Okay.
Actually, now I can see your notes. So whatever you did.
Now you can see, yeah, whatever I did. Okay, so I'm going to stop sharing because, okay, we're going to try this again. Let's, yeah, so it worked before when we tried it, right? So let's just,
yes.
So do you Do you still see the notes?
Just a second. Yes, now I do see the notes.
Okay, I don't know what we did before. Okay, you know what we're going to do? We're going to, what I did before, I think. So I'm just going to, we're going to try this again. I'm sorry for this guy. We did try this and it did work.
Yes,
but,
well, that's how it usually is, right?
Okay, so we're going to try this again. Yeah, what did we do last? That's funny. Okay, here we go. I'm going to share this. And then...
Yes, now there are no notes.
Yeah, okay, but... Okay, are there still no notes? Oh, this is great.
Notes are back.
Okay, well, what do you want me to do? I guess, who knows? I don't know why I've done exactly what I did before, I thought. 1 second. Stop share. There is a...
You have the option to share just individual windows. So there's the share the desktop option, and there is the share sort of a specific window option. That could be the cause.
Yeah, we are going to try. We're going to try this. Everyone's going to see the notes for a second, and then we are going to try. Yeah, there. No, I've got this.
Do you have separate? I forgot what you said. You don't have separate screens, right? You only have one.
I only have one screen, which is the whole problem. And I'm not sharing anything now, right?
Now you're not sharing anything. Yes.
No. PowerPoint slide. Yeah, here I'm just sharing the slide. Yeah, it's funny. It worked before. You saw it. You know. You believe me.
Yes, yeah, I believe so. So this is fine for us. This is what we can. So now we can see just your presentation, but I guess you cannot see your notes like you did before. Is that?
Yeah, I guess we might just have to kind of muddle our way through it, I guess. Well, let's just try it. Okay. So thanks for that introduction, Max. It's almost as if I wrote it myself, and I apologize to everyone for this little confusion getting this thing started. This presentation is something I gave 3 years ago at the Decennial Exploration Conference in Toronto. I want to thank Alan Jones for inviting me to participate in this EMinar. I also really have to thank my co-author, Jamin Crystal, who put in a lot of work getting the accompanying paper together. And for those of you who are interested, there is a lot more to the story than what I'm going to talk about today, and that's in this accompanying paper. I think we have about 4 examples that we're going to show today, but there's probably 11 or so in the paper. So just a brief outline. Again, this is basically what I gave 10 years ago. So I'm going to say 10 years, and really, if you just want to say it's probably more like 13 years ago now. So we're going to start with a little bit about what happened in the past 13 years. And then I'm going to talk a little bit about the mineral system context, which is something that's been around in the oil industry probably for decades, but I think it's really only starting to be appreciated in mineral exploration in the last, maybe even the last 5 years or so. I'm going to talk a little about magnetotellurics. I don't think I need to dwell on that too much to this audience. Then I'm going to talk about ZTEM. And at the time, 3 years ago, there really was only ZTEM. I know there are a few other offerings now. Expert Geophysics has mobile MT to compete against Geotech's ZTEM. We're going to go through 4 examples that I think are good examples of, or the better examples of what MT can do in mineral exploration. And then topics at Exploration 27 is basically just a bit of a crystal ball into the future. and then acknowledgements, and then there'll be a Q&A. And yes, if anyone wants to ask a question during the presentation, I'm happy to stop. I cannot see the little Q&A box or the question box, but Max can. So Max can interrupt if he thinks that's a good thing to do. So the last 10 years has seen increasing uptake of natural source EM methods and the technology, MT, ZTEM, inversion codes. Frank Morrison and Ed Nichols 20 years ago, and of course I don't have the quote in front of me anymore, but they basically said that MT methods are going to become prominent in exploration in the next 10 years. And I basically said the same thing 20 years later. So maybe they were a little early in what they said, but it is kind of deja vu. They based their that statement primarily on forward modeling, because there was so little data around at the time. But fortunately, today we have some data that we can present, and we can show why that statement, it was probably early 20 years ago, but ultimately it's going to be proved correct. I think we have a maturing perspective on physical properties. I think we as geophysicists, and I'll say mineral exploration geophysicists, have always said that mineral physical properties are important, but we've really historically only dealt with them, I'd say, in a qualitative sense. We really don't have the tools, or we're only starting to really develop the tools to put these physical properties into our inversions. But at least we're starting to do that, which is a good thing. And then I discussed this mineral systems concept. I'm just going to read it. It says, mineral system concept focuses mineral exploration strategies on incorporating primary data sets that can map the critical elements of mineral systems at a variety of scales, particularly the region of the camp scales needed to make exploration decisions. And that is key. And it's really what's driving, I'd say, exploration at Anglo-American these days. As we go into a new area, we're really starting to think about, the mineral system, not just finding one little hot spot in a survey, but when we look at the data from a whole region, from a regional scale, what does it mean in terms of the mineral system? So mineral systems have four critical elements, and they're basically fertility, architecture, geodynamics, and then this preservation of the primary depositional zone, right? So the thing gets in place, and then over time it gets eroded or faulted or whatever, and we have to hope that those last things that are done to the deposit, don't destroy it or remove it from the possibility of ever being mined. Yeah, so orogenesis again is really a conjunction of the first things, and this favorable geodynamics. I actually had to look up what was meant by that, and it's really this great catch-all between, geochemistry, math, and physics, and how it speaks to what happens in the mantle, and how that relates to faulting and volcanoes and yeah, everything. So it's a great little catch-all term. Important in the mineral system context is scale dependency, and I'm just going to back up a slide. I think MT has a role to play, in all of these. Well, not so much in preservation, but in A, B, or C has a role to play in all of these, and we could probably discuss and argue what they actually are. But in this table, I've purposely only populated the favorable architecture column. So I'm not trying to say at all that MT doesn't have anything to do with the others. But what we basically see is that on the deeper or the larger scales where we might want to see deeper, we're going to need longer period MT to actually see what's going down. And then as we move up in these scales or in in size. So from a continent to a province, to a camp, to a deposit, we're going to gradually need higher frequency data and tighter spacing so that we can actually resolve what's going on. And of course, playing into all of this is going to be our understanding of physical properties. So again, what we're trying to do is map the mineral system, because we know that even though this porphyry copper deposit has a footprint of maybe only 1 to a few square kilometers, we know that the system that generated it has a footprint of tens of square kilometers at least, and maybe even more. So we really have to be able to hone the tools that enable us to zoom in properly. A great example of increasing the search space, and I guess specifically in mineral exploration these days, we are really going undercover. I think most people would argue or would agree, that most of the outcropping things have been found. But the mineral industry, at least in Saskatchewan, they went through this thought process a good 20 or 30 years ahead of everyone else. So in the 1970s, the Sioux deposits or the Key Lake deposits, they were basically found just by hunting down boulder trains with high uranium anomalies on surface. But then it became, it was always understood that these deposits were associated with graphite, which is a decent conductor. So exploration started to go underground using EM methods. And in the 90s, Cigar Lake and McArthur River were found at about 600 meters. And just as you look at the slide, note on the vertical scale that there is a changing scale there. So Cigar Lake and McArthur River were found in the 80s and 90s using large loop TEM from surface. And then someone had the idea, well, let's do some AMT surveys over them, and lo and behold, AMT, these deposits lit up using AMT. So then, well, as the basin got deeper and active source EM methods started to find their limitations, it really became appreciated that that MT was going to be a tool of choice. So I guess the neat thing, and this is the part about magnetotellurics that you guys all apparently or should know, but the best part is that I think from Canyard that came up was that we could take this ratio of electric field to a magnetic field and come up with a resistivity structure that is independent of the source field and the source structure. So that's great. And at this talk that I initially gave, of course, there were geologists and non-geophysicists in the audience. So I told them how resistivity is proportional to or basically the same concept as getting resistance. Someone has raised their hand. Max, is it? Okay.
Not that I can see right now. Let me double check. No. No.
Okay. Okay. Well, I'll continue on then. So what's key here, though, is that I think if you want to have a resistivity measurement, you need to measure the electric field, and this is going to this did play initially into the airborne methods, and we'll get to that on the next slide. But at the time of this, like 10 years ago, I think some very important but incremental advances were made. So we moved from single acquisition sites to distributed arrays. The electronics got better. The coils got better. So now it's possible to to go out and just lay out one set of coils rather than a high frequency set and a low frequency set. We have the possibility for producing capacitive line antennas, which is important in Canada and in the northern countries if you want to collect data on snow. We know a lot more about remote referencing. And I think we've done a lot on inversion, especially 3D inversion, meshing, and now joining MT with, let's say, ZTEM. And then there have been advances in related fields like controlled source EM as well. So at the time, 3 years ago, there was only ZTEM on the market. I said since then, there's at least one other method called mobile MT. And in the early days of ZTEM, a lot of people were calling it airborne MT. And I can sort of understand why, because it's natural source EM, but I think it was important, and it still is important to say, well, it's not really MT because there's no telluric component to it. It's only the magneto component. And you know, to this day, and I've used this technology a lot. I'm still in awe in the fact that we can measure this dimensionless number and come up with a resistivity structure that is meaningful. And I guess you'd have to say, as long as you do your inversion correctly, and you know, again, we can argue about how accurate it is in terms of the absolute values, but to me, that's probably not as important as just getting the relative story straight. At expiration 2007, so 10 years prior to this one, ZTEM had just come out, and in all the papers in that conference, it was mentioned just once. And by the time 3 years ago at expiration 17, I phoned up Geotech. They said they had surveyed over 370,000 line kilometers. So clearly, in the past 10 years, these airborne natural field methods have become, you know, a pretty important tool in the box for mineral exploration geophysicists. So there I have the delta. The downside of these methods is that the lack of the intrinsic resistivity, and you can't resolve layered earth geology. And of course, there's a limited bandwidth, which has to do with, you know, collecting these data from a helicopter in a moving field, bouncing around. But on the positive side, you can collect large swaths of data, rugged and remote terrains at low cost. Rugged terrains is important because there's no active source. In a rugged terrain, if the helicopter cannot maintain a constant drape, it doesn't really matter as much because we don't suffer from the same detrimental fall off of the field as you would in an active source helicopter survey. Advanced in the past 10 years specific to ZTEM, I'd say our inversion. I don't know how many of you were around when it first came out or were actually looking at these data sets, but Geotech produced 24 plots, basically real and in phase, of the two components for each of the 6 frequencies. And they were, you basically had to put all of these together, and they all looked very different. You could basically ultimately see what you wanted to, or think you could see what you wanted to in one of them, but it wasn't really meaningful. So the fact that they were able to get Phil Wanamaker to write some inversion codes and make sense of those was a huge step forward. So a bit more about geology, factors that influence resistivity within a porphyry copper deposit. This is a study that Nelson and Van Voorhis did in 1983. So we have basically a generalized porphyry after Halley is in the middle, and the data of Nelson and Van Voorhis, which was modified by Lee in 2015, is on the right. And I think there's like something like 137 individual samples in there. And you know what it basically shows is that for less than, let's say, 1 or 1.5% weight sulfides, you basically end up with the resistivity of the host rock. And excuse me, when you get down to, let's say, above 7.5%, so that could be speaking to, you know, high-grade bornite veins at depth, well, then you're starting to see the resistivity of the mineralizations, and then in between, you kind of have this inverse relationship. So, of course, if you pick one data point at random, you don't really know where you are. But if you fly a large survey that covers barren host rock, altered host rock, and then mineralization, you're going to see something like this. And this sort of speaks to, you know, the mineral system concept, which maybe people would obviously have been doing this, you know, 20 years ago or 30 years ago, but it's now sort of being posited in this kind of system process. So examples that I'm going to discuss, the GAWLER CRATON and Olympic Dam in Australia. Sorry, so these are the ones that were discussed in the paper. So we had Olympic Dam. These are all porphyries, and it's the ones kind of in a larger font are the ones that are going to be that I'm going to show examples of. So the GAWLER, Santa Cecilia, Collahuasi, Morrison are the porphyries. Kansanshi and Frontier are Sedex copper deposits in Zambia. MacArthur River is the uranium one, and there are actually two examples in the paper from there. And Voisey's Bay, and that data was interesting. It's not in the presentation, but it's the first time that that it actually been published. So I was lucky enough that I could you know, pull in some cards and approach some mining companies and have them give some stuff that could be published. So on the GAWLER CRATON, this is probably, I think, one of the poster childs for why we need to do big regional MT surveys. This is modified from Graham Heinsohn in 2016, and I'm pretty sure he's published something newer than this. But regardless, it suffices for what I want to talk about today, which is, you know, we have this, and it's, you know, it's quite compelling. And whether we actually understand what it's actually saying to us, I don't know how far along we are along there, but we have this very high conductivity, you know, blob at depth. And that's fluids or some putative magnet chamber? You know, it doesn't, I mean, to me, I guess it is important, but I mean, we see that, and then we see these fingers, and I've heard of people calling them, you know, the fingers of God or whatever, coming up, and they appear under Olympic Dam and Titan and Acropolis. And again, even if we didn't know what this meant, if someone handed you the section and you were an exploration geologist or geophysicist, I mean, it's clear to see where the anomaly is, and where that anomaly is you know, possibly has an expression on surface, and you would go poking around there immediately. So I think these, as we start to collect more data like this, you know, US Array, OzLAMP, Eon Rose in Canada, if it ever gets off the ground, we're gonna, I think, have a chance of making some significant discoveries moving forward. This inset here is, I guess, is an idealized porphyry that comes from Silito. And I mean, again, to me as a geophysicist, you know, I see you know, a great relationship between the two. You know, some geologists think that IOCGs and porphyries are kind of end members of the same system, and some don't. I'm probably in the camp where I do see some sort of relationship between the two, but in this example, I clearly think that there is. But moving on, this is Collahuasi in Chile, and Collahuasi is not really part of the MT story per se, but it is part of the story about how we got here. Everyone knew about Rosario. It was being mined, I guess, in the late 80s. So its high-grade vein system was known, but Uhina, it's actually a supergene enrichment blanket. And like it says there, it was covered by 170 meters of ignimbrite cover. So it was basically blind. Someone decided to run an IP resistivity survey. And there are the lines. And basically, so we got this amazing resistivity blob over Uhina, but at the time, I don't think that people really appreciated that you could have these enrichment blankets. So the first, I don't show it, but the accompanying IP chargeability plot basically has a high around the edge of the resistivity. So they drilled the IP and not the resistivity, because nobody believed that the copper mineralization could be so resistive. So it must be in the chargeability, and they ended up drilling the barren pyrite halo around Uhina. And then it's finally when they had done tons of drilling there and found nothing, someone finally said, okay, let's drill the center of this resistivity blob. And that's where they intersected this this massive supergene chalcocite blanket. So what that did at the time, it really changed the focus in porphyry copper exploration from looking for, the primary mineralization to the supergene mineralization. And all these companies started to fly airborne EM surveys in what they thought were prospective terrains, trying to look for really conductive anomalies. And it probably worked out once or twice, but again, I mean, everyone thought probably that it was going to turn into shooting fish in a barrel, and it clearly wasn't that. But it did help kind of promote our understanding of how these systems evolve. The next example is Santa Cecilia in Chile, and this is an example of a 3D EM survey. Or sorry, a 3D resistivity survey and a subsequent survey, but I'm showing this because it really kind of highlights the story. But this is the DC, so it was a vertically elongated system, multi-phase quartz diorite stocks, intruding volcanic host. In 2010, there was a shallow CSAMT survey that identified a conductive drill target, so that had some grades that were of interest in follow-up. So there's the 2012 CSAMT looking at depth, and then the 2010, and then in 2012 they went back and they did this 3D DCIP or Orion survey, and basically we can see if all you had was that. So the voxel on top is the DC data. If you had that data, and yes, there's a nice resistivity anomaly, it's kind of interest, and you probably would drill it. But if that was accompanied by this deep imaging MT profile, and you see that this thing had legs at depth, it would suddenly become, I think, much more interesting. And it's basically, I think, where we're headed these days. We want to know that our anomalies on surface have some expression at depth, that it's not just a very localized thing. It gives us a lot more confidence into what we need to drill. So Kansanshi is in Zambia, and in Zambia, in these SEDEX deposits, what you end up looking for are these domes, and often you want to look for little bumps on the side of domes. So Chris Wines talks about looking for domes on domes. These two images, excuse me, are at different scales, but you can see the relationship between the two of them. And the MT or the AMT section on the right, is mapping one of these conductive horizons, and it clearly shows a dome. And because it does, it becomes an exploration target. And again, these things are under cover, right? So we could be under 1 to 200 meters of cover for sure here. Morrison, BC. I threw this in the paper because I believe at the time it was probably the first published by Ben Lee and Martin Unsworth from the University of Alberta on a joint inversion between ZTEM and MT. And this is, I think, an important way to go because, I said earlier, the ZTEM data, very easy to collect. You can do it from a helicopter. It's cost effective. It gives a good picture, but again, it doesn't give those absolute resistivities that we like and come to expect from an MT survey. So what happens if you then, go and collect some MT stations? Now you have ground MT stations, airborne ZTEM, so no electric field, and we want to combine these together. There are numerous challenges in doing that, but there are numerous benefits. And Sasaki there says inversion of sparse AMT data was shown to be effective in providing a good initial model for ZTEM. Moreover, simultaneously inverting both data sets led to better results than the sequential approach by enabling the identification of structural features that were difficult to resolve from the individual data sets. So that's why we want to do it. But the problem is that in your inversion, you may end up, let's say, with tens of thousands of ZTEM data, right, where we take each station and the two components and a bunch of frequencies. So you have tens of thousands of these data, and you may only have a few hundred or a few thousand MT data points, right, if you take frequency and in phase and quadrature. So the problem is that if you just throw these into the inversion and don't do anything to the data, you can basically swamp the MT data with the airborne data, and they really don't end up playing a role. So the way this is generally tackled is by addressing the errors. So you try to you put the errors in the MT smaller to sort of force it to pay attention to those. And there he's got the examples of 50%, 20, 10, 5, and 2 on the MT. And I think in this case, they ended up deciding that the 5% error on the MT gave the most reasonable picture about what was going on. There are other challenges when you do the two, and I've experienced a lot of these. Coordinate conventions are very kind of I'll say insidious. East north up versus northeast down. If you mix data sets, you need to get your coordinates sorted out, and you need to transform the data so that they're all in the same coordinate. I spoke about the problem of data density going from thousands of ZTEM, and here I said to tens of MTs. Setting optimal error bars, mesh generation, how we deal with galvanic distortion, how you reconcile the two models together. This, I mean, it sounds really great. I mean, I've had managers and exploration managers come out and said, well, just throw them together, and you know, it sounds easy. You know, maybe conceptually it's easy, but the practice of doing this is certainly not easy. And I wouldn't say that there's a you know, a go-to playbook has been written. So anyone who figures that out, you've got a decent competitive advantage. So in the next 10 years, what are things going to look like? I think we're going to have total field systems like AirMT, 3-component systems like mobile MT, I think we will reduce the lower frequency limit. That's it is kind of an engineering challenge, but I think they will get there. In the ground systems, I think we're going to basically stop insisting on collecting E's and H's and maybe Z's at every single station. We may have E-only stations, H-only stations, so I just haven't used the word, but magnetovariational, right, which is basically what the airborne stuff is, plus or minus tippers. You know, people are talking about having sparse electric stations because those, of course, need access, but being able to put H-only stations from drones and be collecting data in areas that are otherwise difficult to access. Improved capacitive antennas and broadband coils, drones I spoke about. More large-scale surveys. So I mentioned USA Array, OSLAMP. Eon Rose is something that was being proposed in Canada, and according to Alan, it's kind of hit some kind of wall. It's been progressing. Those would probably include airborne magnetovariational data. Better incorporation of hard and soft constraints. And I would say especially we need to learn how to put the physical properties in the inversions. You know, borehole resistivity surveys are great, but if you think about it, you have a mesh that has or a voxel that has 500,000 cells in it, and you have a few holes that each touch 20 cells. You know, how important is that? How can you actually, you know, make those data meaningful? And what do the borehole resistivity data actually mean? They're modulated by the conductivity of the fluid. You might get several readings from 8, 16, 32, 64-inch probe separations, and which one do you use? So I think we need to do a lot more study to really understand how we can use those data, so we can better understand the geophysical expression of the mineral system. So I guess that's it for the presentation. I would like to acknowledge these companies and these individuals. So Anglo American, my employer, for allowing me to take the time, and Jamin's time to write the paper. We got data from Cameco and Arriva, Codelco, First Quantum, Geotech, and Vale, and then there's a list of individuals who Jim and I all had great discussions with, and that helped us write the paper. So I guess that's where I've landed. There's probably tons of time for questions, so I'm happy to sit around and continue this discussion.
Yes, thank you very much, Joel. That was very interesting. So the way we're going to handle this has worked very well in the past. You type your questions in the question and answer box, and we already have one there, and I will read it out, and then Joel will answer it, and that way it will also be part of the recorded version of the talk. So there was one from Jaja-san. For the Morrison example, why does the data misfit keep increasing when MT error estimate decreases?
Okay, we are going to go back to that. I'm going to say specifically, I don't know. I didn't actually do these inversions. I've just sort of copied this section out of the paper. So maybe it's discussed a bit more in there, but I think it does, it goes to show, if you're asking me what I think, this is one section out of a whole 3D inversion. And I do have a problem, it's almost philosophical, but we often focus in on just one number. right? I mean, if you focus in on the misfit, and the misfit is, it could be very good in one place and very bad in another place globally. So I would think that what they've done is they're publishing the misfit, but they've gone through the model and they think that in this line, the inversion is showing the most realistic, I think, sampling of let's say of the model space. But the misfit, of course, is impacted by what's going on all over the rest of the model. So we can't see the rest of the model, but that's what I think.
Well, so NASA McBell actually sort of typed in the answer that I also sort of suspect strongly what's going on here. So in MT, we normalize by the data error. Yes, so the misfit is the difference between observed and modeled, and then we divide by the error. And if they really, actually, regardless of whether they report the sort of raw misfit or something like an RMS, if you assume that your MT error is smaller, your misfit automatically will go up. So, you know, you can, if you want, so if you can turn it around and say, you know, I can fit any data with any model by just making the error large enough. If I assume my MT data is 100% error, everything fits, right? So yeah, and of course, what you said also sort of plays into that. But yeah, so it's a, if you want, a technical issue. Sure.
No, okay, good. No, thanks for that. I don't profess to be a, you know, I mean, I use this stuff in my day-to-day job, and maybe I just know just enough to be dangerous. But
yeah, if I could just jump in here, Max and Joel. Yeah, I think it's more an expression that perhaps the model is not complex enough to handle the MT data. That when the error is high, then the MT is not having much influence. But as you reduce the MT error flow, and I should say error flow rather than error, then the MT data becomes more important, and the model is probably not fine enough to deal with the MT data errors.
Yeah, look, I don't want to, you know, with all due respect to Benjamin Lee, this was a master's, you know, thesis, and someone who, you know, has one project, and for a young guy who doesn't have a wealth of experience doing this, and I mean, it's driven home the point. But I mean, whether this was, you know, we could always spend more time and do more work and refine things till the cows come home. But you know, knowing where he was, you know, he did what he kind of needed to do to show what, you know, to show what he was trying to show, and I think he did that. And now it's probably for the rest of us to you know, to acknowledge, you know, what was done and the challenges that, you know, that he uncovered, that I think a lot of us may have just, without reading this, you know, a lot of people would struggle with a bunch of these things. So he did really good work in advancing what needs to be done, but certainly there's more work to do.
Yes, sure. I think that's true for virtually everything.
Everything we do.
We do, or sort of anybody does, yes. I mean, in academia, even as permanent academics, we have more time to spend on things, but at some point we also have to call it a day. You know, it's good enough. Okay, let's move on to, there are a few more questions. So thanks very much for the very good presentation. Could this method to be used for gold exploration? Do you have some examples?
Okay, could it be used for gold exploration? I mean, I guess everything could be used for it. Okay, so I'll go to the second one. Do I have any examples of gold exploration? No. I think what we really need to understand, and I think we ultimately do for everything, the porphyry copper deposits that we're mining today are 0.5% copper, between 0.5 and 1. And if you remember that I'll throw in, if I go back to the there it is. the figure from Nelson and Van Voorhis. So if you go even 0.5% copper, you're really not, that disseminated copper is really having nothing to do on the resistivity expression. So what happens then, what we're really going for is, so since it's not a primary indication of the, of the mineralization that we're interested in, we're now saying, well, we want proxy. So in the case of a porphyry copper, we start to look for alteration, right? For the propylitic and the phyllic and the clays that are all over the system. And we're going to hone in on those. And that's going to, so that we're going to go from barren outcrop, high resistivity to maybe a moderate or a resistivity broad anomaly that's going to reflect the alteration. And then if we're lucky, we're going to get something really, really conductive, either showing a chalcocite blanket or these bornite veins. So that's how it works in the porphyry space. In the gold space, of course, gold is, I mean, it's almost shameful when I talk to my, friends who ask about mining and you tell them that we mine, ppm of gold. So yeah, you would need to find, you would certainly need to hope that there's a broader system, right, of mineral alteration that you're, that you're seeing, or there are some faults or structures are being shown that could be a pathway. I've got yeah, I mean, I've got some friends and former colleagues who who work for Barrick and in Nevada, and I'm just trying to recall if they've ever mentioned to me doing lots of deep-seated MT, and I honestly can't recall. So it's possible, but I don't think it's common.
Yeah, and again, I think this is something a lot of us certainly, if you don't do this exploration, we don't realize, the minute amounts that sort of you're hunting for, and you think, oh, copper is conductive, so we can find it. But as you said, it's the other stuff that sort of is associated with the copper deposit that shows up. And the same is, or it's even more true, as you said, for gold. So yeah, if you know the system, I guess you can do something. But yeah, I don't know enough about those. Gold.
That being said, I because I kind of lost my notes and I had to ad lib a lot more than I wanted to. There was another quote that I wanted to say, and it was by this guy W. Edward Deming, who I think in the 50s or 60s said, "You can't expect what you don't inspect." And I think it's really key. I mean, what it basically says is that, we can say all these things about what we think is going to happen, but if we actually don't go out and collect the data, then we don't know. And I think one of the things with MT, and going back to what Frank Morrison and Ed Nichols said, whatever in 1997, that this was going to become a very important method, and they did it all on the forward modeling side. It took 20 years before, I'd say, mineral companies actually started to commit some money to doing MT surveys. And now that we are collecting the data, right, we can actually, and we are inspecting what's going on, we can basically more properly tell our managers, what to expect. So maybe there is something in gold. I don't know, but I mean, yeah, someone's going to have to go and collect a big survey over the Carlin, and who knows? Maybe this U.S. array survey, when the data, right, if someone goes and takes a look at the data all over the Carlin trend in Nevada, they're going to see that there are some really deep-seated features like we saw from the GAWLER CRATON in South Australia under Olympic Dam.
Well, I suspect there are, I know NASA is in the audience, so he has a model, I have a model. I think there are various people here who have models of that area. It's just we don't know what to look for. So might be some interesting projects to take those models and have somebody who knows, where these things are to look at it. But yeah, we have a few more questions.
Okay.
So according to your experience, are the rich magnetite rocks beneath the potassic zones or within the potassic zone? Sorry, I need to reread that question. According to your experience, are the rich magnetite rocks beneath the potassic zone or within the potassic zone?
Geez. Look, I'm a geophysicist. That's probably low. Look, I'll admit that's probably getting a bit more, almost a bit too geological, technical. I mean, in my mind, I associate the potassic zone with the magnetite, but the porphyries are so complicated. They've been reworked, you know, so many times, so many fluid pulses. So of course there is, you know, what was primary, and the magnetite is often primary and then often gets destroyed. So I've seen potassic zones with strong magnetization and potassic zones with no magnetization because it's all being destroyed. So I guess I've seen, I've seen the whole gamut, and but yeah, you're probably going to have to ask a porphyry expert about you know, which came first. Yeah, sure. So related to that, how do you deal with magnetic susceptibility in the magnetite zones and magnetotelluric data inversion? Okay, I'm going to say that right now we completely ignore it. That would be my guess too. I mean, if you're using one of the, let's say, at least semi-published MT inversion codes and not some secret source, I think they're all at the moment ignore that. Yes. Yeah, but you know, I mean, I guess you ignore things at your own risk. So, I guess if you know, if someone thinks that that we need to do this, you know, that right, if you have rocks down there that are you know, 0.05 SI, which is fairly magnetic. I mean, if that's going to make a difference, I guess we need someone to tweak one of these codes and shows that it makes a difference. I mean, you know, that's probably something that's a worthy study. And even if it shows up the negative, I mean, I think it's worthy for someone to say, hey, we thought about this and we tried it out and it didn't make a difference. But then we wouldn't ask these questions anymore. So I encourage someone to pick up that torch. Yes, no, definitely. And then also, okay, there's a large IP effect in porphyry deposits. Is there any useful study about the effect of IP on MT data porphyry mineral exploration? So I guess similar to the magnetic question. Yeah, you know, I would be really interested in, you know, in learning about that. I mean, I guess if you just think that the IP response is actually kind of a phase shift, right, at those low frequencies now, and we know, you know, historically this whole 2 seconds on, 2 seconds off for these resistivity IP surveys is basically so that survey ends up right in that low frequency MT deadband, right? So they did that to sort of get away from that. But we know that most surveys we do, the IP anomaly has not died out over the 2 seconds. So then we end up, you know what happens. I mean, if you turn the transmitter back on before the anomalies died out. So yeah, it kind of gives you the wrong answer. So we know that we've seen IP anomalies that are existing if you use something like 16 seconds on and 16 seconds off. So certainly as we push the frequencies lower in IP, and of course, why don't we do it in IP? Because the survey takes too long. So, you know, from the scientific point of view, it's great. I mean, I would love to have this IP journal, but as we push the survey, the IP survey longer and longer, it probably turns more and more into an MT survey. So I'm going to guess that there is an effect. Yes, although, and this is some really vague memory of mine. I think I saw a presentation where somebody looked into this, and my recollection is, as I said, very vague, that it's very small for the MT when you actually do then the whole processing and so on. And I forgot why that is, but that's my yeah. Memory. I mean, I would say the other thing that may make it more difficult in the MT space, though, is that I think our stations generally tend to be further apart. Especially if these are kind of right, and it makes sense because we're not, no one really does an MT survey over a deposit until you found it. So you're doing very wide space stuff because you want to understand the general structure, but that makes it hard, if a lot of the survey is, or if a lot of the data is a bit more near surface, or right, it makes it a bit more challenging, I think, to relate adjacent stations.
Yes.
So you could have an effect in one sounding, and you don't have it in the adjacent soundings because they're a kilometer away. And then is it noise or is it signal? So you really don't know.
Yeah. Okay. A few more questions coming in. So Raha Hafisi, considering the fact that MT resolution decreases below conductors, how much can you rely on the MT results below conductors? Or how can we be sure that the results are real? I think that's a everlasting question.
Yeah. Good luck. Yeah. I don't know. I mean, I guess at one point in what I do, you just have to recommend the what we call the rotary lie detector. You just have to drill it.
Well, that's certainly one way. I mean, yeah, there are techniques, right? I don't know how much of that you employ of doing sensitivity testing and sort of testing if certain features are really required by the data or just have popped out because of some idiosyncrasies of the inversion.
We do try to do that, as best we can. Yeah, I mean, I didn't really touch about forward modeling in this presentation, but it is something that we do, we do try to do. And of course, it's always a bit of a caveat because you come up with some model or structure in your head, and then you model it and you go, well, if this exists, well, yes, I can see it, but it's really, if it looks like this, I can see it, right? And because our forward models, of course, never explore the entire space, right? Just the ones that we tend to hone in on. I think that's just the reality.
Yeah, and so we can, if you want to test certain hypotheses, I think that's the way how I look at it. Is if it looks, as you said, if it looks like this, then that's what we see, and maybe that looks a bit like what we actually record or not. Okay, and then the second question also by Raha, can we say MT never gives us the exact solution and we always need another method to constrain?
Yeah, I think I would agree with that. As soon as we throw in errors and the vagrancies are inversions of our inversions. I mean, I think we've probably all done inversions where you flick one little switch and you get an answer that's radically different, and then you're trying to explain which one is it. So it is important to take MT data with MAG data, which we hopefully have, and some the geological data that we have, and compile all these data sets to make really an integrated interpretation. No one method is a smoking gun. So I would agree.
Yes, and I mean there are a few comments now about previous questions. For example, Patricia De Luguao says no method gives the correct answer, and you have to combine methods with knowledge of geology. And I mean, geologists also, I mean, if you want to say, we mean sort of educated guesswork, right? You extrapolate from the surface and you put it all together to the best of your knowledge and try to make sense of it. I think that would be my take on that.
Yeah, exactly. I mean, that's what, if it was just the method and you plunked it in some inversion code and an answer came out, most of us probably wouldn't have jobs, or we wouldn't need to have jobs because.
Well, and that's what I always tell my students as well when they get frustrated. Yes, it keeps us in business, all those difficulties.
Yeah.
There were a couple of also comments from Leo Fox and Darcy McGill about gold exploration. So Leo says, Mike Dentith presented a poster about 3D MT over the Gruyere Archean Archean orogenic gold deposit in Western Australia. Appears to show a mineral system signature. And Darcy McGill says, CSAMT has been used extensively in South America for epithermal gold exploration to map resistive zones associated with silicification. So I guess that's sort of also what you said, right? We look for, not for the gold, but for what's around it.
Yeah, you're looking for the mineral system. I know in South America, we used to do lots of resistivity surveys. The same thing. You get this alunite and this massive quartz. So you get these resistivity anomalies in the hundreds of thousands of ohms. I mean, it's great when you find them.
Yeah, and okay, I missed one. Sergio Espinosa also sort of mirrors that sentiment, if you want. So we're not mapping commodities. You map basically the geological conditions or the geological system, the geological environment, and then sort of interpret that. So just wanted to mention that. Then a question by Shungo Wang about MMT. I suppose that's mobile MT.
Yeah.
I'm curious if the MMT can record high quality data at long periods, as good ones as the ones at ground. What's the longest period it can record?
Yeah, I haven't had the opportunity to use it yet, so I don't know. Sorry, you're gonna have to. Yeah, you'd be better off speaking to them or someone who's had some experience with it.
Yeah, I mean, my guess, don't have first-hand experience either. Is you were talking a little bit about this with the ZTEM as well. You have the thing dangling from a moving object, right? So I think long periods are certainly 100 seconds is you would have to hover with your helicopter in one place for quite a long time to get 100 seconds at a certain point. So you're talking sort of hertz generally. But yeah. Okay, a few more. Do you have any advice about chromite deposit exploration with using EM methods?
I'm going to have to be honest and say no. No. I actually, I've looked for a lot of commodities. I've never looked for chromite.
Yeah. And again, I guess it really depends on the geology of, what these chromite deposits are associated with and how they
Yeah,
form.
and then kind of the regional signature. So we know that a porphyry copper deposit, like I said, the actual deposit has a fairly small footprint, but the footprint of the magma chamber that caused it is probably 10 to 50 times bigger, right? So you can actually look for a big thing and then try to hone in. So it all, what's the size of the chromite deposit? What's the size of the system that creates it? If they're kind of one and the same or close, it would be difficult. If the system is spatially large, then there's a decent chance that there's going to be some conductivity signature of the Earth that is either going to reflect the host rocks or some architecture. Just go back to that first slide on the mineral system on this one.
Yes. And then we're approaching, at least for the moment, the last two. So Sayed Foroshani, don't you think inversion of Tipper vector from MT gives better results than inversion of impedance? So Tipper rather than impedance.
I think so, but why don't I let the experts answer that question? So do you want to answer that, or Alan, do you want to pipe in?
Well, so my experience with this is, yes, Tipper gives you a lot of good sort of lateral information, but the electric fields, and I think you said this also in ZTEM, I mean, it's a similar thing, right? The absolute resistivity is certainly more difficult. Also, in terms of practical I tend to see that certainly coil measured tipper tends to be quite noisy. I think with long periods, sort of the flux gate measured tipper, probably because it's a bit more stable, it seems to be better. But very often when I have coil-based data and it contains tipper, the tippers are of, let's say, okay quality, whereas the impedance can be much better.
Yeah, I think that's true, Max, at low frequencies, but certainly at mining frequencies, you know, the flux gate doesn't work at 100 hertz. You're only going to use coil data. But generally, generally people have to remember that tipper, the vertical field is only responsive to anomalous structure. And so any conductivity structure that's slowly varying laterally will have quite a weak tipper response. And the advantage that tipper brings is it does have this great sensitivity to edges, to the charges on the boundaries of conductive edges. And so in the past, tipper inversion alone has produced things where you've got unconstrained depths, and you need the electric field, as you said, in order to give you absolute value.
Yeah, and just to clarify what I said, of course, in the mineral exploration context, you don't have a choice but to use coils, but because they're long and bulky and usually difficult to bury completely into the ground, I think that they tend to be more affected by movement and noise, and then that's what you see with the tipper. At least that's my impression.
Yeah, that would make sense. Well, I mean, I think being on the survey end and yes, it can be difficult to get a good site for a Z coil, for sure.
Yeah. Okay, and then last question from Jan Avram. Great talk, thanks, Joel. Historically, mining companies had exploration programs focusing at deposit scale. Is the mineral system concept changing the way mining companies are thinking the exploration program? Are we to expect more regional programs in the next few years?
You know, I don't know if I can speak for the industry as a whole, but I'd say that Anglo-American is certainly, you know, taken the mineral system concept to heart. And really, I mean, ideally, I would think that the whole industry sort of has to. When you stake ground, you know, you don't just stake, you know, what's going to end up being the deposit. You stake a whole whack of ground. And these days, especially with things under cover, the tenements that you take are huge. Like, you know, you can go and take Angola, right? Some company goes in there and takes like 40,000 hectares in Angola. Well, I think we really have to do better than just bump hunting the results from the survey. Because yeah, I mean, everyone's going to focus in on the bumps, but it really has to be put in this context. Even if you have, you know, if you have one bump, well, it's pretty easy. But if you have 100 bumps, well, which is the bump? And then you really need to step back and scale and look at other things and say, well, you know, I think that these are the bumps that are important. It's kind of like, you know, we know that you know, someone talked about magnetic susceptibility and potassic zones. Well, okay, you can go. So I'm going to you know, look at a map of Chile, and I'm going to flag every single mag high, right? I mean, it doesn't really work. If you did that, you would be at it for hundreds of thousands of years. You really need to know, you know, that the West Fissure is the zone, and then okay, well now I'm going to start to focus on bumps within the West Fissure or you know 10 or 20 kilometers on either side of it, and then I'm going to focus in on bumps that are within that West Fissure corridor, but are also on you know a cross-cutting structure as well, and then you're going to hone in. But I mean, it's really, but you really do that because you appreciate more than just the airborne mag survey. You have to put it in the context of the geology and the context of the system. I mean, I probably can't say that, you know, importantly enough.
Yeah, and okay, there's a final comment, and I think with that we'll finish, from Sergio Espinosa again. So comment to Jan's question, exploration pipelines start with generative exploration on a belt scale. I think that's sort of also mirroring what you just said. Yes, you have to find your target zone before you can then actually start looking in detail.
Max, before we let Joe go, can I ask him to tell us, what does industry need from MT and what does industry want from MT? Because there's a lot of students and academics working on developing the method, and we think we know which aspects need to be progressed. But what is the perspective from industry about what's important? Is it more sensors on the ground? Is it better processing codes? Is it better inversion codes? Just tell us, Joel, what you would like to, what you think MT needs to do, and what you think it should do over the next few years.
Yes. No, you know, everything. Look, I think, you know, the industry, I mean, well, it all depends on, you know, who's the audience. If the audience is my exploration manager, they don't really care about the processing code. They just want it to be, you know, to be processed well. I think what we're still working towards is getting more budget, basically to collect more, you know, to collect more stations. We get permission to go out and collect a station every 5 kilometers, for instance, right? So Anglo American has staked a huge tract of ground south of Mount Isa, and we're doing these you know, these big regional surveys. And yeah, I mean, it's all scale dependent, but I think what I mean, ultimately, you know, what you would like to have is maybe twice as many stations will actually just confirm your you know, your interpretation. But aliasing is still a big, like spatial aliasing, I think is still a big problem. So what we actually need is I think more examples of where this, you know, this technology is working. The presentation and the paper, you know, show MT surveys over some specific targets. So that sort of allowed us to move out, right? We showed, okay, look, I mean, if we know where it is in hindsight, we can go and do the survey and we can find that mineralization. Okay, well, now we're excited, or at least now we're confident that the survey will do as it, you know, as it does. But then we need to go and collect data in a lot of places. And now we have a lot of anomalies. So now we have to sort those out. We go back into the mineral system, but what other corroborating things? I mean, if I have an anomaly at a kilometer depth, what else can I really do to, or other surveys can I do to corroborate that? You know, maybe mag, but it depends on the, you know, on the terrain. Your conductivity anomaly may not have a big mag expression. So seismics would be great, but it's even more money. I'd say the mineral industry is even further behind on seismics than we are in MT. Although I think a lot of this passive seismic or ambient noise tomography is sort of starting to make a run. So I think what we need is more examples. I mean, I think these regional surveys, the section through Olympic Dam, you know, when you show that to an exploration manager, they get pretty excited. Then when you ask them for the money to go do it somewhere else, they get less excited. But that's what we need. I think we really need some examples. You know, I think the inversion code and the processing, all those little blocks, they're all going to be developed, you know, over time. But what we really need is some decent stories so that we can maybe get you guys some money to build these blocks a bit quicker. Does that make sense?
Well, yeah, certainly. Okay, actually, that one last question has popped up, and I feel it's interesting enough that I don't want to leave it out. And that was, how did you manage to collect high quality data or data at all in an operating mine? And for those examples.
Oh yeah, well, you probably don't really if the mine is operating. I mean, I guess on the magnetic side, you may get a little lucky. I know in Voisey's Bay, if you go into the paper, they shut down. Now, I don't think the mine was in full operation, but they shut down the major power lines, like, right? Not just the little ones, but like the big trunk lines. They basically shut them down for for a couple hours every day so that they could collect these data. I mean, if the unfortunate reality about mines, well, maybe not so much now that they're undercover, but once they were found, the power line was always run down geological strike to the mine, right? It's just the way it was. You go to Sudbury, yeah, right, because the strike is probably like some sort of resistant feature, so it's a great place to put a power line. But then the first thing the mine says is, well, go look down strike, and yeah, well, you've built this huge power line, so it's really problematic for active source EM, and it's even a bigger problem for natural source EM.
Yes.
In my experience.
Yeah, no, and I think it is a problem. Certainly data I've seen that you see patches whenever you approach infrastructure that becomes poor quality to unusable.
Yeah.
Okay.
I know that. Sorry, I know that some of these. I know that Jerry Holman and Kennecott in the 70s, when they were doing all these porphyry surveys in mines, and especially these small ones, like when they were trying to develop spectral IP, so they were doing like 3 foot or 6 foot pole dipole or dipole dipole surveys. They used to wait for the mine to go on strike because that was the only time they could get into the pit and it was quiet. So. Yeah. Not that I'm advocating a labor disruption, but I mean, you have to take the take the chances that happens. A big ice storm happens in Canada and knocks down all the power lines. It's probably a good time to go collect some MT data.
We'll take that into consideration. Yes. Yeah. Well, thank you very much. That was very interesting. Certainly, also for me, who's been a little bit exposed to this world, but maybe not that much. So with that, yeah, thank you again, and we'll sort of close the EMinar for this week. And next week, I said it in the beginning, forgot it now. I think it's Paul with US array. Is that correct, Alan?
Yeah, I think so. I've not gotten back yet.
Look on the MTNet website and you'll find out, or maybe you have a better memory than me and remember what I said at the beginning. So yeah, thank you very much, everyone.
Yeah, Paul Bedrosian at 1600 UT.
Okay.
Okay. Thank you.
Yeah. Thanks very much, Joel.
Yep. Bye-bye.
Bye.
Bye.